Today we will solve the problem 2.38 of Griffith 4th edition, Introduction to Electrodynamics. The problem 2.38 is a metal sphere of radius r carrying charge q is surrounded by a thick concentric metal shell of inner radius a and outer radius p as shown in the figure. The cell carries no net charge. Then find the surface charge density sigma at the point R and A and at P. So this diagram shows the sphere of radius R. This radius is R as shown in the figure. This is radius is R. The sphere carries the charge q, and we have there is a metal outer concentric shell for which the inner diameter is a and the outer diameter is p. This outer one is p. And net charge inside the cell is 0. There is no net charge. So under these circumstances, what is the sigma r? Sigma r is sigma r, that is surface charge at surface r is equal to q, total charge divided by area. Here this sphere carries the charge q, so naturally this a is 4 pi capital R square. So this is the surface charge at QR. Then remember that I will do something. Remember that here it is a positive charge. The surface of sphere has positive charge. Naturally, the inner surface will have the induced negative charge, and outer surface of this cell will have induced positive charge. So that here the net charge will be 0. So what is the charge at the inner surface? Is a negative charge. So q by a is equal to minus q over 4 pi a square. Similarly, the outer surface, that is sigma p, is equal to, you can use same q by a, which is equal to, here it is plus. So plus q divided by 4 pi p square. So we have answered for the subdivision A. Then we will go for another subdivisions. Section P is find the potential at the center using infinity as a reference point. You take infinity as a reference point. So we have to find the potential at the center, that is at the origin, where the origin is 0. So we have to find V of 0. So by definition, V of 0 is equal to minus integral between infinite to 0. So, that is the electric field when we are bringing the charge from infinite to 0. Infinite to 0. This we can split separate into three regions. First one is coming from infinite distance to P. Infinite to P, that is one region, and another region is P to A. So this is P to A. Then another region is A to R. Then next is R to 0. There are four regions. So this potential at a point 0 is equal to minus integral between 0 to infinite. This sorry, integral between infinite to p. This up to this point, E dot tr. Then next is A to P, between A and P. This is P, lower limit is P, upper limit is A. P to A, E dr minus this from A to R. So A to R, E dr. then similarly R to 0, next region is R to 0, then E equal to E integral between R to 0 E dot dr. Now you can see what is between A to P. The A to P there is no charge, you know. Between A and P net charge is 0. So this integral will be 0. A to P is 0. Then what about this 0 to R to 0? Here from R to 0, the electric field will be is 0. This will be 0. Because there is no charge enclosed inside it, so it will be 0. Only first and third. First, between infinite to P, at P you have charge Q. I have explained in the previous section. This is having positive charge, and inner is negative charge, and this surface is positive charge. So positive charge, this positive charge induces the negative charge, and this negative charge induces the positive charge. The net charge inside this concentric cell is naturally 0. So we have applied all the conditions. The first one from infinite to P, from infinite to this point P is equal to, electric field is equal to Q over 4 pi epsilon naught R squared TR R cat. This R cat unit vector indicate the direction, that's all. Then next A to R, from A to R, because A to P is 0, then A to R, you will have this surface charge Q. So that is here you have minus A to R Q over 4 pi epsilon naught R square TR. Now if you differentiate 1 over R square, you will get to minus 1 over R. So minus of minus will become plus. This will become Q divided by 4 pi epsilon naught R. Similarly here 1 over R squared will become minus 1 over R, which will become plus Q divided by 4 pi epsilon naught R. Now we have to apply the limit. So here first case the limit is infinite to P. The next one, the limit is A to R. So first apply the, you can take 4 pi epsilon naught outside. Then what about this? If you apply the upper limit, this will become 1 over P. So 1 over P. If you apply the lower limit, this is 1 over infinite is 0. So you can neglect it. Here if you apply the upper limit, you will get 1 over R. If you apply the lower limit, you will get minus 1 over R. So this is the potential at the point at the origin, that is V at 0. We have seen that surface charge at the inner sphere is plus positive charge, and the surface charge on the inner surface of this cell, concentric cell, is minus. The outer one is plus. Now what you are doing is you are grounding it, grounding the outer surface. So you are grounding this outer surface. Naturally, the charge will get is drawn by this ground. So there will not be any charge at the outer surface. So what is the effect on sigma A? Sigma A retain as it is, because at point A you have negative charge. So this will be as it is. You will have this as it is. And what about this surface at sigma P? Sigma P, this will be 0 naturally, because you are grounding it. This will be 0. So what is the potential in that case at point 0? V of 0 is equal to, you will get this 1 over P. At the point P it will be 0, so you can ignore. You need not do it again, just to you take the result of section P and cancel this 1 over P, because at the point P the charge is 0. So you will get the answer as 1 over R, 1 over R, 1 over R minus 1 over A, 1 over R minus 1 over A. So this is the answer we got. So thank you very much for watching my video and supporting me continuously. Thank you very much.